Hi guys, Miss O'Connell here. So I'm gonna start out today by moving myself to the other side of the screen, but also talking about a few points to consider or review on your lab before you turn it in on Monday. So again, the Hooke's Law lab is due Monday, as I had a few students incorrectly do part one and needed some time to redo part one and then take a look at part two. So looking at our data thus far, this is the data table that represents the hair tie clementine system that I showed you in the previous video. We can see when we enlarge this graph here that the data points do not fit the linear trend line. Some of us will have a few data points that fit the linear trend line, okay? If the data points fit the linear trend line, the system follows or obeys Hooke's law. Hooke's law states that the restoring force and the stretch distance will be proportional to each other, meaning that the rigidness of the material, also known as the spring constant, will stay constant or consistent throughout each trial. If the data points do not fit the linear trend line, that means that force and stretch are not proportional. If force and stretch are not proportional, we cannot determine the spring constant consistently. So if we take a look at this graph here, I have 1, 2, 3, 4, 5, 6, 7 data points. Not one of those 7 data points fit the trend line. If you take a look at your spring mass system graph, I'm going to use a student example to demonstrate that. So this student had already handed the lab in, so I'm going to use their graph as an example. So we can see that 1, 2, 3, 4, 5, 6, 7, maybe this one's a little bit off, so let's say 6. 6 out of the 7 data points for the spring mass system fit the linear trend line, while none of those 6 data points fit the trend line for the elastic band or rubber band system. So what that means, right, if these data points fit the trend line, that means that this slope is consistent. If we take the slope between any two of these points, we will get 5.81 newtons per meter. So the spring constant of the spring is consistent. It's a consistent 5.81 newtons per meter. Why? Because the majority, 6 out of the 7 data points, fit a linear trend line, which demonstrates that force and displacement are in fact proportional, which is exactly what Hooke's law states. On the other hand, the elastic band system, on my graph, none of the 6 matched up with the trend line. If we take a look at this student's graph here, it's a little bit hard to tell from the size. I'm going to open up the document so we can see it a little bit larger. Okay, there we go. So here we have, make this a little bit bigger so it's easier to see. I'm also going to put the legend inside the graph so that the graph is less smushed. Another way in which we could expand the graph would be to move it to its own page. But I'm going to change the legend to inside of the graph so that might be easier for us to take a look at. And again, move myself to the other side. Nope, that's not gonna work. Oh, there we go. Here we go. All right, so we can see here that I would say that maybe this point is on the line. And I would say that maybe that last point could be on the line. Again, it's hard to tell unless we move this to its own sheet and really take a look. Okay, yes, I would definitely say that this point here brushes the line, and so does this point here. So there's 2 out of 1, 2, 3, 4, 5, 6, 2 out of 6 points that fit the trend line. Okay, versus on my graph, I have 0 out of 6. Okay, some of you came for extra help. We looked through your data, you had maybe 1 out of 6, okay, that fit the linear trend line. So if the majority of the data does not fit the linear trend line, then the system does not follow Hooke's law. If the data points do not fit the linear trend line, that means that force and stretch are not proportional. If force and stretch are not proportional, it does not follow Hooke's law. Okay, so based on my hair tie system, this almost looks like, I would say, a polynomial curve. So probably some function x squared. Okay, so maybe 1/2 kx squared, something similar to that. You'll notice here that there are drastically different values for k for the elastic bands. So even if we were to use the exact same elastic band, there would still be some variation in the k that we measure here. Does anyone think they know why? Okay, so if the data points don't fit the trend line, that means that k is not consistent. As more force is applied, the rigidness of the material will change. Okay, the rigidness of a spring is constant, but the rigidness of an elastic band or a hair tie will change depending on how much force is applied to it. Therefore, these values for k, they're not great estimates of the spring constant of the elastic band. They're not very consistent. Okay. A few other things I want to point out about the student's lab who had already submitted it. So make note and adjustments before you submit Monday. Again, make sure you have your hypothesis statement in there. Okay, if then because statement. Perfect. Okay, so our student also included the part 2 of their procedure, so I understand how they collected their data. So if there is any error, I can understand where that came from and why. Then we have our data tables. Underneath our data tables are images of our graphs. An advanced step would be to label those graphs. See how this says data table 1 spring mass system? You could call this graph 1. Graph 1 spring mass system. Okay, and graph 2 spring mass system. Okay, notice the guiding questions here. Please make sure that you use data as evidence. Your answer to these guiding questions should be at least 2 sentences each, and they should include data. So please make sure that before you submit your lab, that you go back and you look to make sure that you included the data. The spring constants, whether they're consistent, whether the data points match the trend line. So use your graph, your data table, and the slope of your graph. Incorporate those into your analysis questions. Okay, so hopefully we kind of have an idea of how we determine whether material is elastic and how we determine if the spring constant is consistent based on the data set. today we're going to be talking about elastic potential energy, which is an expansion of our previous unit, conservation of energy. And it actually is related to the lab that we just did. So we're actually going to forego the do now for today, but feel free to give it a try if you'd like. Okay, so as I said before, this fits in with our previous unit of conservation of energy. So we're going to talk about a specific type of potential energy, okay, elastic potential energy. Elastic potential energy is present or stored whether a spring is being compressed or stretched. So whether it's compressed below equilibrium or above equilibrium, it will store elastic potential energy based on its position. Okay, so it can be stretched or compressed and still store elastic potential energy. If the spring is at equilibrium, it is not storing elastic potential energy. We see here in classic cartoon, Roadrunner, that the energy stored in that spring is converted to different types. In the explosion lab that we did before we left school, right, the elastic potential energy stored in the plunger cart was converted to kinetic energy so that the carts moved away from each other in the collision. Same thing is occurring here. Elastic potential energy, the compression of a spring, is being converted to kinetic energy. Okay, and then eventually that kinetic energy will be transferred to gravitational potential energy, which will then decrease until the cartoon character hits the ground. Okay, other examples of this would be one of my favorite things to watch, which is pole vaulting. Okay, so the athlete runs. While the athlete is moving, he has kinetic energy. That kinetic energy is harnessed into the pole, which stores elastic potential energy, which is then converted to gravitational potential energy as the athlete soars into the air. Once he is released from the pole, all the elastic potential energy is gravitational. Then that gravitational kinetic energy is converted back to kinetic. Other classic example would be a bow and arrow or a slingshot. Okay, so by pulling back the bow, you're storing elastic potential energy. That elastic potential energy is then converted to kinetic energy. Okay, so we can model elastic potential energy with an equation. The elastic potential energy is given by the equation U sub S. So again, we use U for potential. S stands for spring. Okay, U sub G was gravitational potential energy. U sub S is elastic potential energy, measured in joules. That's equal to 1/2 times K. K again is our spring constant, measured in newtons per meter. It tells us the rigidness of the spring, so how much force per meter of stretch. That's multiplied by the displacement, or the stretch/compression distance, squared. We use the variable x to represent that. The units for displacement are meters. When we take newtons per meter and we multiply by meters squared, we still have newtons per meter, which is technically equal to a joule. Okay, so that's where our units come from. Based on our lab practices for the past week, right, we know that K varies, the spring constant varies. So every system will have its own independent spring constant. The elastic potential energy depends on that spring constant, as well as the displacement. So in order to increase elastic potential energy, the spring constant and the distance stretched would also need to increase. Let's take a look at what the difference between stretch and compression would be in a spring mass system. So I'm going to use a simulation to help us do that. So here we see, which we've seen before, a mass attached to a spring. Here we have a bar graph showing the potential energy, the elastic potential energy. We notice that when the system is in equilibrium or rest, aka there's no stretch or compression, there's no elastic potential energy. As we increase the stretch, aka as we stretch the spring, the potential energy will increase. So when we displace the spring by a meter, the potential energy will increase. If we compress, meaning we move it to the left of equilibrium, if we compress the spring a meter, we still have elastic potential energy of 50 joules. Energy is a scalar quantity, meaning that it does not have direction. It will not be negative. So whether the spring is compressed or stretched by a meter, the elastic potential energy is the same. It has the same potential, okay, regardless if it's a negative or a positive stretch. Again, so looking at that equation, right, U sub s equals 1/2 kx squared. Another way in which we can increase the potential energy is by increasing the spring constant. So to maximize elastic potential energy, we need a large displacement and a large spring constant. To minimize, we want a zero displacement, or as close to zero as we can get. And a small spring constant. Okay. So let's try a few examples. I'm gonna move my camera here. There we go. Can I make it smaller? That's flipping it. Oh, now I'm full screen. Okay, I'm gonna move it up here to the top right corner. Hopefully it won't, actually move it to the center of the screen. Hopefully it won't affect the visuals here. So let's try an example. Okay, so elastic potential energy. Example 1. To store exactly 1 joule of potential energy in a spring, for which the spring constant is 20 times 10 to the 4 newtons per meter. How much would the spring have to be stretched beyond its equilibrium length? So basically here we are given the amount of elastic potential energy that the system stores. So we determine that elastic potential, U sub s, is equal to 1 joule, based on its position. The spring constant, the rigidness of the spring, is equal to 20 times 10 to the 4 newtons per meter. So what that means is that we have 2 and 5 zeros newtons per meter. So a very, very large spring constant, 200,000 newtons per meter to be exact. How much would the spring need to be stretched beyond its equilibrium length? So we're looking for x, our stretch distance. So if we have elastic potential energy, we know how much energy is stored based on its position, and we have the rigidness of the spring. We can use the elastic potential energy equation to determine its position. So we're going to plug in what we know. So our elastic potential energy is equal to 1 joule. That must be equal to 1/2 times our spring constant, which is 200,000. To fit it on the screen, I'm going to write it in scientific notation. 20 times 10 to the 4 newtons per meter. And then we're going to multiply by x squared. So we're leaving what we don't know as a variable. Ooh, that looks like a monster M. That should be an M. Okay, so we need to simplify. We'll pop out our calculator, which I know you have handy and ready to go. You can either type in 200,000 or 20 times 10 to the 4 into your calculator. Either way works. Remember, if you're using scientific notation, you use the EE button, which comes out as just a capital E. So I have 0.5 times 20, e to the 4th. I'm going to press enter. I get an answer there. I now need to divide both sides by that value. So I'm going to take 1 joule divided by 100,000 for second answer. And I get 1 times 10 to the negative 5, which you can either leave in scientific notation or write it out. We'd have 0.00001 in case you move the decimal place to the left 5 times. That's equal to x squared. Our units here get a little tricky. So we have, I'm going to do this over here on the side in a separate color. We technically have joules, right? And those joules are being divided by newtons per meter. Okay, so we know that a joule is equal to kilogram times meter squared times second squared. Sorry, hopefully you can read this. It's very difficult to write with these online tools. So I have kilogram meter squared over second squared. That's all divided by newtons per meter. We technically know that a newton, F equals MA, right? A newton would be kilogram times meter over second squared. Mass times acceleration, right? The units for mass are kilograms. The units for acceleration are meters per second squared. The units for joules, right? If you take a look at the equation, newtons per meter times meters squared, that simplifies to kilogram meter squared per second. And that quantity, this is a Newton, right? So we need to replace Newton with its definition. That quantity is still divided by meters. So focusing just on the denominator, right? One of these meters will cancel out. We have meters divided by meters. Okay, so we have kilogram over second squared in our numerator now. I'm going to do this step by step. We now see, right, that we have kilograms that will cancel out. Our second squared will also cancel out, right, if we were to multiply top and bottom by the reciprocal. Second squared over kilograms. To simplify our fraction, right, second squared would also cancel from both terms, and we're left with just meters squared. So that is our units for the left-hand side of our equation. To find that position, we need to get x by itself by taking the square root of both sides. We find that that position is 0.03 meters. So very small. I want you to think about why that makes sense. So why does that solution make sense? Or does it make sense? Okay, so we know that this equation relies on spring constant and the stretch or compression distance, right? If spring constant is very large and elastic potential energy is very small, in order to account for that, the stretch distance must be small because the product is rather insignificant, right? 1 joule of potential energy. So it makes sense that if the spring constant is very large and elastic potential energy and spring constant are proportional, the displacement, meaning the compression or the stretch, must be small in order for the potential energy to be relatively small. So this answer does make sense based on the relationship between stretch, spring constant, and elastic potential energy. So 1 joule of potential energy is stored in this spring when it is compressed or stretched by 0.03 meters, which is equivalent to 3 centimeters. Okay. So this is taking a little bit longer than I expected because of the discussion about the lab. So after this example, we're going to stop and we'll finish up the examples on Monday. So next week's going to be pushed around a little bit compared to the schedule that we discussed in class on Wednesday. Okay, so example 3. When a 4 kilogram mass is hung vertically on a certain ideal spring, meaning that it follows Hooke's law perfectly. That's what the word ideal means. It stretches 2.5 centimeters. Find the spring constant. So I want you to pause the video and do this part A by yourself. This is a review. So you've had lots of practice doing this. Please pause the video and give it a try. You can press play when you have your answer. Okay, so what we should have gone through, our first step here would be to write down our givens. Right, we know mass is 4 kilograms. We know that the stretch distance converted to meters would be 0.025. We need to find the spring constant. Ideally, we would use Hooke's law. In order to use Hooke's law, however, we need the restoring force. So how can we find the restoring force? Well, Newton's second law. So when we draw a free body diagram for our mass, we sum the forces in the y, we find that the restoring force, or the force applied by the spring, would be equal to the object's mass times gravity, right? That's the definition of force of gravity, the object's weight. Mass times the acceleration due to gravity. We'd get that the restoring force is 39.2 newtons. Now that we have the restoring force, we can use Hooke's law to find the spring constant. And we find, or we plug in, for restoring force and displacement, which is below the equilibrium, therefore negative. We divide both sides by that displacement to get spring constant, which will be 1,568 newtons per meter. Okay, so that is a review from last week, and that is part A. So now we're going to use part A to find out information about the elastic potential energy. So in part B, we're asked to find potential energy. What is the potential energy stored in the horizontal spring mass system when it is stretched to 11 centimeters? So our first step here would be, again, to write down our givens. So we know that x is now 0.11 meters. What do we know will stay constant in the system? So think, which variable can we assume will be the same? That's right, spring constant, right? As long as the material stays the same, the spring constant will not change. Okay, so our givens for part B. X is 0.11 meters. K from the previous part is 1,568 newtons per meter. We need to find U sub S, the elastic potential energy. So lucky for us, we only have one variable to solve for, and we can use the elastic potential energy equation to do that. So our next step would be to write that down. I have U sub S is equal to negative 1/2 K times X squared. Excuse me, no negative sign. I'm not sure why I said that out loud. So U sub S is equal to 1/2 kx squared. We're going to plug in for our k and our x value and solve for mu sub s, the elastic potential energy. So I have 1/2 times 1,568 newtons per meter times 0.11 meters squared. First thing that I need to do in my calculator is type in that displacement, 0.11 squared. You get 0.0121. I'm now going to multiply that by my spring constant, 1,568 newtons per meter. Finally, I will multiply by 1/2, or 0.5. And we get that the elastic potential energy stored will be 9.4864, which we're going to round to 9.49. And what are our units? Our units are joules. Okay, so we have 9.49 joules of energy stored in this spring due to its stretch or compression distance of 0.11 meters. All right, so that's it for today. I will see you guys or talk to you guys on Monday. Enjoy your weekend.